Hey scientists, this is Physical Science, Semester A. This is the Unit 2 test review. We're going to talk about motion. We're going to do some multiple choice questions that are great practice for the test. If we're talking about a change over time, think about the DIRT formula here, distance equals rate times time. And we're talking about a change in your position over time. Which one of these things shows a change in your position over time? Distance, rate, or time? So is that slowing down, distance over time, speed in a certain direction, speeding up, or rate? Change over time is a rate. It can be measured using distance over time. Distance over time is one example of a rate. There's a great little video on how to use the DIRT equation to figure out rates or speeds. It's a race between aliens, and I'll put that in the notes. Speed is an example of a rate. How do we measure speed? How would we measure how fast this bobsled is going? This bobsled is probably going about 80 miles per hour, and miles over hours is distance over time. And there's a difference between speed and velocity. Speed doesn't have a direction. It's kind of like just going fast with a blindfold on, which is why I showed this kid blindfolded. She looks kind of miserable. If you were going really fast with a blindfold on, you'd be kind of miserable too. That's speed. Now, if we're going to talk about velocity, velocity knows where it's going. These ladies pushing this bobsled know exactly where they're headed. So velocity, you know where you're going. It's different than speed. So if you know where you're going, that's speed in a certain direction. We can express velocity as a vector quantity. A vector has a magnitude, size, that's how fast you're going, and it shows direction. So magnitude and direction equal a vector. Acceleration is slowing down, distance over time, speed in a certain direction, speeding up, A and D. Think about your car. You have two pedals in your car. If it's an automatic, one is for speeding up and one is for slowing down. So A and D, acceleration in your car is how fast you can change your speed. When you put your foot on your accelerator, you speed up. Your speed changes, you go faster. If you look at the speedometer, the speedometer, measuring your speed, it increases. If you put your foot on the brake and look at the speedometer, your speed decreases pretty quickly. So acceleration is the brake and the accelerator, slowing up and speeding down, or speeding up. All right, let's see if we can match these quantities. What things go with speed, what things go with velocity, and what goes with acceleration? Let's think about just what we've talked about so far. We know that speed is distance over time. And one way you can express distance over time is meters per second. If that meters per second, how fast, if we want to know how fast that is changing, we express meters per second per second. That's acceleration. Another way to say meters per second is meters per second squared. So both these things go with acceleration. Speed goes with meters per second, or distance over time. Velocity, of course, if you add direction, that's velocity. Change in velocity over time, or change in your speed and direction over time, is acceleration, which is the rate of change of velocity of an object. So how fast something is speeding up or slowing down is the acceleration. Pause the video and see if you can mentally match all of these things. So here are your answers. Take a minute to look at this and think about it. Pause the video again and make sure you understand why things are connected here. Why speed is meters per second, change in distance over time, etc. Let's talk about slowing down a little bit. It's a lot slower to go skiing in the summer because grass has more friction. If it's wet, it gets a little bit more slippery, but grass has a whole lot more friction than snow. Friction is a good idea for this parachute jumper. The air molecules are slamming into his parachute and slowing him down. Air resistance is one example of friction. Forces slow things down. A force can be described as a push, as shown in this airplane how to get the door open directions, or a pull. Or it's a good way to move a box. One person can pull and the other person can push. So forces are a push or a pull and they move things. If you want to go to an almost frictionless area, we all know here in Minnesota that sliding doesn't involve a whole lot of friction. So snow and ice can decrease your friction. It's a bad thing if you're trying to drive. And space can also reduce your friction. So space and ice are great places to do almost frictionless experiments. If you start moving on a frictionless surface, think about air hockey tables. Air hockey is not, of course, a frictionless surface, but it's much less friction than a normal table. If you hit an air hockey puck, what happens? Does it continue moving until it's stopped by an equal and opposite force? Does it stop after a few minutes or until it runs out of table, or nothing can cause you to stop? If you hit an air hockey puck, it's going to keep moving. And it might be stopped by an equal or opposite force. Maybe your opponent here is going to hit it back, put some force on it. Or maybe it'll run into the wall here and meet an equal and opposite force and change direction. If you want to get something moving, of course, you have to apply a force. The bigger the object, the more force. This guy can exert probably a whole lot of force. If we apply a force, the more massive an object, do we need more force to move it or less? Or the same amount? Does weight not matter? If you were going to pick up this giant pumpkin, would it take more force or less force than this little tiny plastic ball? If you guessed more force, you're correct. You know from real life it takes more force to move a couch than a penny. It's proven by Newton's law. This is not an immovable object, but it would take a lot of force to move that huge, heavy object. If we're going to compare the force it takes to move a couch versus a penny, we can use Newton's second law. F equals what? The force in your house is often your ma, which you spell MA. What does that MA stand for? F equals MA stands for the mass and acceleration. The force needed to move an object to overcome the acceleration due to gravity depends on the mass. So let's go back to here to the mass of the couch here is larger, so you're going to need more force to move the couch because of the mass of the couch, and you're going to need less force to move the penny because the penny has less mass. Both are being accelerated by gravity at this point, and to overcome that acceleration, you're going to have to exert a force that depends on the mass. If an object is basically in a frictionless place, does it still take energy to get it moving? Yes, yes sometimes, or no, never. Well, think about the tennis balls in space. If they're just floating there in space, are they going to move? Nope, not unless you apply a force. So it always takes force to get something moving, even if it's in a frictionless space. If you were on the ice rink and threw 50 pounds of hockey gear to your right, you'd basically be applying a force to yourself. So which direction would you head off in? If you threw gear to your right, you would go to your left because of Newton's law. Every action, there's an equal and opposite reaction. Throwing gear to your right is kind of like pushing off a wall to your right. How do we know these things? Because people actually study the forces applied to people on skates. Physics folks are studying the force applied to ice skaters, figure skaters in this case, as they jump and twirl and hit the ice. They're looking at the forces that are involved and how much their bodies have to absorb. So if you throw gear, it's a lot like pushing off a wall. You're basically pushing the gear just like you would push a wall. That's why you go left. Newton's third law, every action, there's an equal and opposite reaction. This force is related to an object's mass. So how much force this ball is going to exert depends on its mass. This is a steel ball, and this is a plastic ball. And you can guess which one's going to exert more force. And that's because of the planet we live on here. Gravitational force acts on your mass. The common name we use for gravitational force acting on your mass, that measurement, is what we're going to do a lab on in Unit 3, but you probably might measure the gravitational force acting on your mass in the morning on one of these things. If you guess that that's your weight, that gravitational force acting on your mass is weight, you're correct. You're pressing down, or gravity is pulling you down to the earth, and the earth is pushing back up with an equal force. That is, if you're not in quicksand or soft snow. This force results from charged particles. Here's an example of the force we're talking about. Charged particles in this magnet cause it to have enough force to be able to pick up chunks of metal. If you guess that that's electromagnetic force, you're absolutely correct. It's caused by charged particles, electrons and protons. If you go to a different planet, you're going to have a different weight. Your mass will be the same, but your weight is going to differ because the gravitational force is different. Momentum is, remember, has two quantities from the lab. If you guessed its mass and velocity, you're absolutely correct, because a train is going to hurt a whole lot more than a fly, even if they're moving at the same speed, because the train has more mass, it has more momentum. If you have two balls, a 5 kilogram ball that's moving at 5 meters per second north, and a 1 kilogram ball that moves at 10 meters per second south, which is going to have more momentum? A cannonball here or a softball? The 5 kilogram ball is going to have more momentum because it's 5 times 5. It's the mass times velocity. And that 5 kilogram ball has more momentum, so it's going to resist the change in motion even more. That resistance to the change in motion is because this 5 times 5 has more momentum than 1 times 10. A 5 kilogram ball has more momentum because it's more massive and it's moving faster. An object with high momentum either is moving very fast or is very heavy. It resists changes in motion. Things that are very heavy, they have a lot of momentum, and things that are moving very fast have a lot of momentum. Remember, momentum is mass times velocity. So these are things that are hard to stop. Thanks for watching.